Welcome all. So today's session we will discuss about an important frequency related parameter of op-amp, that is slew rate. So what is slew rate? Slew rate is the maximum rate of change of output voltage with respect to time, usually specified in volt per microseconds. Volt per microseconds. So maximum rate of change of output voltage with respect to time. Okay, so if we tell what is 1 volt per microsecond, okay, 1 volt per 1 volt per microsecond, then 1 volt per microsecond slew rate means that the output rises or falls no faster than 1 volt every microsecond. Okay, so 1 volt per microsecond slew rate is the output, that is output voltage rises or falls no faster than 1 volt every microsecond. And practically we get the slew rate ranges. Practical range of slew rate is for our ICs are usually rate of slew rate is 0.5 or not 0.1 microsecond, 0.1 volt per microsecond. Okay, the practical value will be 0.1 volt per microsecond to 1000 volt per microsecond. 1000 volt per microsecond. Okay, so ideally actually we need the infinite value for this slew rate, so that the op-amp output voltage would change simultaneously with the input, but it is not possible. So the practical range will be between 0.1 volt per microsecond to 1000 volt per microsecond. But there is exceptional cases also. There is some ICs that created for the studies of slew rates only. So in that type of ICs, the value must be increases to 6000 volt per microseconds. Okay, but usually we are not using that type of ICs for the practical purposes. So these are the main ideas of slew rate. Now we will see what are the changes according to the slew rate in the case of closed looped gain and the supply voltages, and when we apply some temperature to ICs. Okay, so that is shown in the next picture. You can see closed loop gain versus slew rate, supply voltage versus slew rate, and the temperature versus slew rate graphs here. In the first graph you can see when the closed loop gain is increased, slew rate also increased, and the supply voltage is increased, slew rate also increased. So the two properties that is directly proportional were the closed loop gain and the supply voltages. But when when we apply temperature, what will happen to the slew rate? It is slightly decreases with the increase in temperature. Okay, so you can see here in the case of temperature only, there is inversely proportional. They are inversely proportional. When increase in temperature results to a decrease in slew rate. Okay. Next we will discuss the causes of slew rate. Okay. Causes of slew rate. So in the case of slew rate is a process in which we consider the large signal phenomena. Usually bandwidth and transient responses, all these are small signal high frequency limitation phenomena. But the slew rate is a large signal phenomena. A large signal is one whose amplitude is comparable with the power supply. That's why when we apply when we increase the supply voltages, what will happen to the slew rate? It will also increase. So large signal phenomena is the directly proportional to the power supply voltages. Typically we can say that the large signal is on the order of volts, while a small signal is in the range of milli or even microvolt. So another thing is slew rate is caused by current limiting and the saturation of internal stages of an op-amp when a high frequency large amplitude signal is applied. Then the resulting current is here is the maximum current available to charge the compensation capacitance network. Okay, so we know that the capacitor requires a finite amount of time to time charge and discharge. Okay, this means that the internal capacitors prevent the output voltage from responding immediately to a fast changing input. That is the limitation we will see in the many of the circuits. We know that many of the circuits already have some capacitors for compensation capacitor network. So capacitor requires a finite amount of time to charge and discharging. Okay, so this means that the internal capacitors prevent the output voltage from responding immediately to a fast changing input. So the rate at which the voltage across the capacitor rises, we can write it as dVc by dt will be equal to 1 by C. And thus the slew rate limiting is caused by mainly this capacitor charging rate. Okay, in which the voltage across the capacitor is the output voltage. So the voltage can be is in the range of 1 by C. Okay, so the capacitor is the main cause of decreasing the value of slew rate. Okay. So next we will discuss the slew rate equation. Okay, for slew rate equation we can consider the voltage follower circuit. Okay, so that is drawn here. Okay, this is the voltage follower circuit. Voltage follower circuit. So you can see here there is a 741 IC is here. Okay, 741C, and non-inverting terminal is the input is given to non-inverting terminal, and output is feedback to inverting terminal. So this is a voltage follower circuit. In the output so what we given to the input, that we will get the output of the op-amp. So that is V0 equal to V in, that is written here, and you can see the output diagram also. What will be the input, and the same way we get into the output as such. Okay, so this is the output waveform, and we will find out what is the slew rate equation according to this circuit. Okay, so we know V0 will be the input what we applied as the input, so V0 will be equal to V. So we will write the equation for both V in and the, what we will get into the V0, that we have to find it here. Okay, so the equation for the sine wave is, so we are applying the input as a sine wave, so equation for the sine wave is V in equal to Vp. Vp is the peak voltage. Okay, Vp sine omega t. So this is the equation 1, and we know what will be the output will be. Output is equal to input itself. So V0 equal to V in. So we can write V0 will be equal to Vp sine omega t itself. Okay. Then we have to find the slew rate. So slew rate is the rate of change of the output. So the rate of change of output is dV0 by dt. So which will be equal to Vp, the rate sine omega t dt. The differentiation term will be what we will get? Yeah, cos omega t. Omega cos omega t. So this is equation number 3. So the maximum rate of change of output occurs when cos omega t will become 1. Okay, so we can reduce this equation to dV0, write it here, dV0 by dt, the maximum rate of change of the output occurs when dV0 dt cos omega t will be equal to 1. So dV0 by dt will be, we can write it as max. Okay, will be equal to Vp omega. Okay, so this term we will call it a slew rate. Okay, the maximum rate of change of output is called as slew rate. So maximum rate of change of output occurs when cos omega t equal to 1. Then we will get dV0 by dt equal to Vp omega, that is slew rate will be equal to Vp omega. Okay, and we can write the omega term. Omega will be what? 2 pi f. Okay, so I just expand the omega, so 2 pi f Vp so slew rate will be, the equation is 2 pi f Vp, and we know the slew rate is expressed in the terms of microseconds. So for that arrangement, this is now in volt per seconds only. Okay, the unit will be volt per seconds only. So I will just write the will take this equation to microseconds time. So there is some arrangement, 2 pi f Vp divided by 10 raised to 6. So that is slew rate. Okay, so this is the equation for slew rate, and the unit will be volt per microseconds. Okay, so here the unit is volt per microseconds. Unit is volt per microseconds, and here unit is volt per seconds only. So this is the equation for finding slew rate in a circuit. Okay. So next we will study the effect of slew rate in applications. So the main applications for find out slew rate is in the case of open loop configuration. So the circuit I have drawn here. This is the open loop configuration using 741 IC, and here I shown the input and output waveforms. So you can see here for IC 741 we are applying the voltage is 15 volt plus VCC and minus VCC. Okay, 15 volt. So the input is applying here, it is a V in. That is I have drawn here as a sine wave that you can see here, and the peak voltage is VP, that also shown here. So in the case of open loop configuration, the gain is very large. Okay, so what will happen to the output will be go to about 14 volt. So if we are applying the input as plus 15 volt and minus 15 volt, the input is gain is very large, so we can say that the output will be go nearly to the input voltage. So almost it will come to the 14 volt. Okay, so I have drawn in the output, it is as plus 14 volt and minus 14 volt. That is the peak voltage will be almost the voltage will be 28 volt. Okay, so 28 volt will be getting in this output voltage that is drawn here, and we will do some effect of slew rate in applications. And here the drawn the picture is of open loop configuration. Okay, open loop configuration using IC 741, and this is the input and output waveform. Input and output waveform. Okay, so I already said that the output voltage is here, we will get it as 28 volt, and the IC 741 as the slew rate is in the range of 0.5 volt per microseconds. Then we can calculate the what will be the time. Okay, here from using the equation, and the slew rate will be slew rate of IC 741 is 0.5 volt per microseconds, and here the total voltage will be from the plus 14 volt to minus 14 volt. So plus 14 volt to minus 14 volt. The time we have to find the time taken by the output to go from plus 14 volt to minus 14 volt can be determined by using these two values, that is 28 volt divided by 0.5 volt per microseconds. Then we will get it as 56 microseconds. Okay, so this is the value, this is the time taken by the output to go from plus 14 volt to minus 14 volt. That I will show in this graph. That is, this is the plus 14 volt and it will go to minus 14 volt. So this time will be the 56 microseconds. Okay, so I will just show it here. So this is the time, this in between this it will be 56 microseconds. Okay, so this is, this value is the 56 microseconds. Okay, so the time taken by the output to move from plus 14 volt to minus 14 volt, that we find out from here, that is 56 microseconds. Okay, then this 56 microsecond must be the minimum time between the two zero crossings. Hence the maximum input frequency f max at which the output will be distorted is given by, we can find out the maximum frequency f max frequency at which the output will be distorted is given by f max equal to, we will get this from the equation, from the slew rate equation. Okay, so f max equal to 1 by 2 56 microseconds from this equation. So that will be 8.93 kilohertz. So therefore the at f max the output may be a triangular instead of square wave. That you will see here in the picture. The input waveform is in the sine wave format, and this 14 volt up to 14 volt, this will become a triangular shape. So up to this much the value will be that is 8.93 kilowatts f max. The output may be a triangular instead of square wave. Thus, to have more square wave output, so what we have to do, keep the input frequency below f max or choose an op-amp with the faster slew rate. So that's why when you construct some circuit, you can see when we increase the input voltages or input signal, what will happen, the output will go to the triangular shapes. Okay, so there is some value or critical value that we can say according to the particular op-amp's slew rate, the output will be exact square wave, or after that frequency, what will happen, it will go to the triangular shape. So here you can see the up to 8.93 kilohertz or below that it will be a square wave pulse, or after that it will move to a triangular wave circuit. Okay. So thank you. This much about slew rate, and you have to prepare the note for the same. Okay, thank you.